December 17, 1941, Aberdeen Proving Ground, Maryland, 8:23 a.m. The Army Ordnance Colonel stopped counting at malfunction 47, overwhelmed by the catastrophic failure rate of the weapon America's entire air defense doctrine depended upon. Colonel Rene Studler, Chief of Small Arms Development and a veteran of 2 decades designing military weapons, stood in the freezing test bunker watching M2 Browning machine guns jam, overheat, and fail at rates that made them operationally useless. 10 days after Pearl Harbor, with Japanese forces advancing across the Pacific and German U-boats sinking ships off the Atlantic coast, the United States faced a crisis nobody outside Aberdeen understood. The .50 caliber machine gun, mounted on every bomber, every fighter, every anti-aircraft position, couldn't sustain fire longer than 60 seconds without catastrophic malfunction. What Studler didn't know was that the solution to America's most critical weapons failure would come not from military engineers or ordnance experts, but from a 48-year-old Tennessee farmer with an 8th-grade education who would discover a technique so counterintuitive that ordnance officers would call it impossible, until it saved the air war. The Browning M2, a weapon military procurement officers had called the finest heavy machine gun ever designed. But in December 1941, as America mobilized for global war, the gun that was supposed to defend bombers and shoot down enemy aircraft was failing at rates approaching 40% during sustained fire testing. And across every branch of service, Army Air Forces, Navy, Marine Corps, the same desperate question circulated. How do you fight a war when your primary defensive weapon doesn't work? The story begins not with the M2's problems, but with a design so brilliant it created expectations the weapon couldn't fulfill. 1918. John Moses Browning, the most successful firearms designer in American history, perfected a heavy machine gun that changed warfare. The Browning M1921, chambered for the new .50 caliber BMG cartridge, was a scaled-up version of his already successful .30 caliber M1917 machine gun. The weapon used Browning's recoil-operated mechanism. The force of firing drove the barrel and bolt rearward together. Then the barrel stopped while the bolt continued rearward, extracting the spent case and cocking the firing mechanism. A return spring drove the bolt forward, stripping a fresh round from the belt and chambering it. The cycle repeated as long as the trigger remained pressed and ammunition fed. The design was mechanically elegant. Fewer moving parts than competing designs meant greater reliability. The short recoil system generated less mechanical stress than gas-operated alternatives. The weapon achieved cyclic rates around 450 rounds per minute, fast enough for effective fire, slow enough to conserve ammunition and maintain barrel life. But the M1921's revolutionary feature was the cartridge. The .50 caliber BMG, Browning machine gun, fired a 660-grain bullet at 2,900 feet per second, delivering over 13,000 foot-pounds of muzzle energy. This was 5 times the energy of the .3006 rifle cartridge. The round could penetrate light armor at 500 yards, destroy aircraft engines, and remain effective beyond 2,000 yards. No other weapon combined the M2's firepower with its relative portability. The gun weighed 84 pounds, heavy but manageable compared to artillery or larger weapons. The Army adopted the M2 in 1933. The weapon equipped anti-aircraft units, armed armored vehicles, and provided heavy fire support for infantry. By the late 1930s, as aviation speeds increased and bomber armament became critical, the M2 became standard defensive armament for American bombers. The B-17 Flying Fortress mounted 13 .50 caliber machine guns. The B-24 Liberator carried 10. Fighter aircraft like the P-47 Thunderbolt mounted 8 M2s in the wings. This deployment strategy, saturating American aircraft with .50 caliber machine guns, reflected the doctrine that defensive firepower would enable bombers to fight through enemy interceptors. German bombers relied on speed and altitude. British bombers flew at night to avoid fighters. American doctrine was different. Heavily armed bombers flying in defensive formations would destroy attacking fighters through concentrated fire. The strategy depended absolutely on M2 reliability. But the M2 had a fatal flaw nobody understood until combat exposed it. Sustained fire caused barrel overheating. The .50 caliber BMG cartridge generated tremendous chamber pressure, 55,000 psi, and propellant temperatures exceeding 3,000 degrees Fahrenheit. After approximately 60 seconds of continuous firing, barrels heated to temperatures that caused ammunition to cook off, ignite from residual heat rather than firing pin impact. Timing became erratic. Headspace, the gap between the bolt face and barrel, changed as metal expanded, causing failures to extract or failures to chamber. Within 90 seconds, most guns experienced complete stoppages requiring barrel replacement. The problem was understood theoretically, but hadn't seemed critical during peacetime. Training doctrine emphasized short bursts to conserve ammunition and maintain accuracy. But combat was different. Bomber gunners facing determined fighter attacks needed sustained fire, 10, 20, 30 seconds of continuous firing to track and hit fast-moving targets. Multiple engagement sequences during a single mission meant barrels experienced repeated heat cycles without time to cool. After Pearl Harbor, as combat reports arrived from the Philippines and Pacific operations, the scale of the problem became clear. Gunners reported M2s failing during critical engagements, leaving aircraft defenseless. Some bombers returned with every defensive gun inoperable. Loss rates for bombers with failed defensive armament were catastrophic, approaching 80% when attacked without functioning guns. Army Ordnance initiated crash programs to solve the overheating problem. Engineers tested alternative barrel steels, experimented with different chamber dimensions, and modified gas systems. Nothing worked. The fundamental physics were insurmountable. The .50 BMG generated too much heat too quickly for any air-cooled barrel to sustain continuous fire beyond 60 seconds. Which brings the story to a civilian machinist in Germantown, Tennessee, who wasn't supposed to solve military weapons problems. John Ed Browning, no relation to the weapons designer, owned a small machine shop manufacturing agricultural equipment and custom tools. Browning had an 8th-grade education, no formal engineering training, and 0 military experience. But he understood metal and heat. His shop produced precision parts requiring tight tolerances, and he'd spent decades solving practical machining problems through trial and error. In early 1942, Browning heard from a cousin who served as a B-17 waist gunner about the M2 overheating problem. The conversation was casual, a family member complaining about equipment failures. But something about the description troubled Browning. The problem as described, barrels overheating during sustained fire, seemed solvable through better heat management. He requested technical specifications for the M2 through a contact at a local Army depot. What Browning recognized, and what ordnance engineers had missed, was that the headspace problem wasn't caused by overall barrel temperature, but by differential heating. The barrel's chamber area, where the cartridge fired, heated faster than the rest of the barrel. This created uneven thermal expansion. The chamber expanded more than the muzzle end, changing headspace during firing. Standard ordnance procedure called for setting headspace when the barrel was cold. As the chamber heated and expanded, headspace increased beyond specifications, causing extraction failures. Ordnance engineers had attempted to compensate by setting a tighter initial headspace, but this caused failures when the gun was cold. Nobody had solved the timing problem. Headspace had to be correct both when cold and when hot, but thermal expansion made this impossible with fixed settings. Browning's insight was simple. What if headspace was set when the barrel was hot instead of cold? The idea seemed absurd. Every firearms manual specifies setting headspace with cold barrels. Hot metal expanded unpredictably. Setting critical tolerances on hot metal violated basic machining practice. But Browning recognized that the problem wasn't the heat, it was the transition from cold to hot. If headspace was set when the barrel was already hot, at operating temperature, then thermal expansion wouldn't change it. He tested the theory on a demilitarized M2 he'd acquired. Browning fired the gun until the barrel reached operating temperature, approximately 500 rounds. Then, while the barrel was still hot, he adjusted headspace using precision gauges. After the barrel cooled, he fired again. The headspace when cold was too loose according to specifications, but as the barrel heated, headspace tightened into specifications. At operating temperature, the headspace was perfect. Browning fired test sequences that would have destroyed a conventional M2. 200 rounds continuous fire, brief pause, another 200 rounds. The gun functioned flawlessly. Headspace remained within specifications throughout the heat cycle. Malfunctions dropped to near zero. Browning wrote to Aberdeen Proving Ground in March 1942 describing his technique. The letter was dismissed. Ordnance engineers noted that setting headspace on hot barrels contradicted established procedure. The technique couldn't work because thermal expansion was unpredictable. The letter was filed with hundreds of other civilian suggestions that arrived weekly, well-intentioned but technically naive proposals from people who didn't understand military weapons engineering. But Browning was persistent. He contacted his cousin, who mentioned the technique to the B-17 unit armorer. The armorer, desperate for any solution to the chronic gun failures, tried Browning's method on several guns. Failure rates dropped dramatically. The armorer reported results through channels. Squadron maintenance officers tested the technique. It worked. By May 1942, word had spread through informal networks. Armorers were setting M2 headspace hot instead of cold, achieving dramatic reliability improvements. The practice violated technical orders and official procedures, but it worked. Units deployed overseas began adopting the technique despite lacking official authorization. Aberdeen Proving Ground finally conducted formal testing in July 1942. The results were unambiguous. M2 guns with headspace set at operating temperature maintained reliability through sustained fire sequences that destroyed guns set to specification. Failure rates dropped from 40% to less than 5%. Barrel life increased because thermal stress was distributed more evenly. The technique worked exactly as Browning had claimed. But ordnance bureaucracy moved slowly. Technical manuals require revision. Training procedures need updating. Official doctrine couldn't endorse a technique that contradicted decades of established practice without extensive validation. The formal authorization process would require months. Combat units didn't wait. Armorers adopted hot headspacing universally by late 1942. Every airbase, every armored unit, every anti-aircraft position received unofficial instructions. Set M2 headspace with hot barrels. The technique spread through practical demonstration. Armorers teaching other armorers, gunners sharing techniques that kept their weapons functional. The impact on air combat was immediate and decisive. B-17 and B-24 bombers conducting daylight raids over Europe suddenly possessed reliable defensive armament. Gunners could sustain fire through entire engagement sequences without gun failures. German fighter pilots, accustomed to exploiting periods when bomber defensive fire slackened due to gun malfunctions, discovered American gunners maintaining continuous fire throughout attacks. The psychological effect was significant. Bomber crews gained confidence in their defensive weapons. Previously, gunners had rationed ammunition carefully, knowing their guns would fail during sustained fire. With reliable weapons, gunners engaged earlier and sustained fire longer, forcing German fighters to break off attacks sooner. German loss rates increased. Luftwaffe combat reports from late 1942 onward noted higher fighter casualties during bomber intercepts. The shift was attributed to improved American gunnery training, larger bomber formations providing mutual defense, and fighter escorts. Nobody recognized that a fundamental change in defensive weapon reliability had altered the tactical equation. The statistical evidence was compelling. American bomber loss rates peaked in mid-1942 at approximately 6% per mission, unsustainable for sustained operations. By early 1943, loss rates had declined to 3 to 4%. Multiple factors contributed, but post-war analysis identified reliable defensive armament as among the most significant variables. Bombers with fully functional defensive guns survived at twice the rate of bombers with partial gun failures. But the hot head spacing technique revealed something more troubling about military procurement and weapons development. The solution to America's most critical weapons failure had been discovered not by military engineers with advanced degrees and extensive resources, but by a civilian machinist with 8th-grade education working in a small Tennessee shop. The technique was simple, required no new parts or expensive modifications, and could be implemented by any competent armorer with basic tools. Yet military ordnance engineers hadn't discovered it. The failure wasn't stupidity or incompetence. Ordnance engineers were highly trained professionals working systematically through potential solutions. But they were constrained by established doctrine, formal procedures, and assumptions about correct practice. Setting headspace on cold barrels was how firearms had been assembled for decades. Questioning that fundamental procedure required thinking outside established frameworks, exactly the kind of lateral thinking that formal engineering training often discourages. Ed Browning wasn't constrained by formal training. He approached the problem empirically. The gun fails when hot, so test solutions when the gun is hot. The approach violated procedure, but the procedure wasn't working. His contribution wasn't discovering a complex solution, it was recognizing that the existing solution was wrong. Army Ordnance eventually recognized Browning's contribution. He received official commendation in 1943, along with a small monetary award. Technical manuals were revised to incorporate hot head spacing as a standard procedure. Training courses taught the technique to new armorers. By 1944, the practice was universal across American forces. But Browning received none of the recognition the contribution deserved. No public acknowledgement, no national press coverage, no post-war fame. The technique was classified during the war to prevent enemies from understanding why American defensive armament had suddenly become more effective. After the war, the improved M2 reliability was attributed generally to improved maintenance procedures, without mentioning Browning's specific contribution. The M2's enhanced reliability influenced far more than air combat. Ground forces equipped with M2s discovered the weapon could sustain fire support during extended engagements. Anti-aircraft units could maintain continuous fire against attacking aircraft without guns failing at critical moments. The weapon's effectiveness in every role increased because reliability increased. The M2 became America's longest-serving military weapon. Introduced in 1933, the gun remained in frontline service through Korea, Vietnam, both Gulf Wars, and Afghanistan. Modern M2s, still in service nearly a century after the design was finalized, incorporates refinements and improved materials, but retains Browning's original recoil-operated mechanism. And every M2 manufactured since 1943 has been assembled using Ed Browning's hot head spacing technique. The technique's longevity demonstrates its fundamental correctness. Military weapon systems are replaced when superior alternatives emerge or when changing tactics render them obsolete. The M2 has survived because it works, and it works partially because a Tennessee farmer recognized what ordnance engineers missed, that the solution to overheating wasn't preventing heat, but accommodating it. The broader lesson extends beyond weapons design. Military organizations face a persistent tension between expertise and innovation. Expertise provides systematized knowledge, proven procedures, and reliable results. But expertise also creates orthodoxy, established practices that resist questioning even when circumstances change. The most valuable innovations often come from outsiders who aren't constrained by expert consensus. Ed Browning wasn't smarter than Army ordnance engineers. He simply approached the problem differently because he wasn't trained to approach it the same way they were. His contribution was recognizing that how we've always done it might be wrong, and that testing unconventional approaches might reveal better solutions. This pattern recurs throughout military history. Radar development was pioneered by scientists working outside traditional military establishments. Blitzkrieg tactics were developed by junior officers challenging established doctrine. The atomic bomb required recruiting physicists who had never worked on military projects. Transformative innovations typically emerge from unexpected sources because expertise, while valuable, can blind organizations to alternatives. The irony was complete. The military establishment that had dismissed Ed Browning's letter in March 1942 spent the rest of the war depending on his technique. Every B-17 gunner, every tank crew, every anti-aircraft battery relied on weapons that functioned because a civilian without military training had noticed what experts missed. The weapon that defended America through 5 wars and countless conflicts remained operational because someone without military training asked a simple question: what if we're doing this wrong? Colonel Rene Studler, who had stood in the Aberdeen test bunker in December 1941 watching M2s fail catastrophically, supervised the formal adoption of hot head spacing in 1943. He never met Ed Browning, never acknowledged publicly that a civilian had solved the problem his engineers couldn't. The official history credited improved maintenance procedures developed through systematic testing, technically accurate but incomplete. Browning returned to his Tennessee machine shop and continued manufacturing agricultural equipment. He never discussed his contribution publicly, never sought recognition, and died in 1957, largely unknown outside his community. His obituary mentioned his machine shop and community involvement, but not the technique that had saved thousands of lives and influenced the outcome of history's largest war. The M2 Browning machine gun fires today with the same reliability it achieved in 1943. American forces in Iraq and Afghanistan mounted M2s on vehicles and emplacements, sustaining fire during engagements lasting hours. The guns functioned reliably because every barrel was assembled using Ed Browning's 80-year-old technique. The soldiers firing those weapons don't know his name, don't know the history, and don't know that their weapon works because a civilian without military training discovered something that military experts had missed. In military museums today, M2 Browning machine guns sit on display, their technical specifications and combat history carefully documented. The placards describe John Moses Browning's brilliant design, the weapon's service record, and its technical characteristics. No mention of Ed Browning or the technique that made the weapon operationally viable. What the placards don't explain is that military effectiveness depends not just on brilliant design, but on practical implementation. The finest weapon ever designed becomes useless if it fails in combat. The M2 was a brilliant design, but it required a farmer's insight to become operationally reliable. The combination of expert design and outsider innovation created the weapon that defended America for a century. The lasting lesson isn't about the M2 specifically. It's about the value of questioning established practice, the importance of empirical testing over theoretical assumptions, and the recognition that solutions can emerge from unexpected sources. Military organizations invest billions in research, employ thousands of engineers, and conduct extensive testing. All of this is necessary and valuable, but it doesn't guarantee optimal solutions because expertise creates blind spots. Ed Browning's contribution was modest in scope, a single technique improving one weapon's reliability, but the impact was strategic. American air doctrine, ground combat effectiveness, and defensive capabilities all depended on M2 reliability. The weapon that didn't work in December 1941 became operationally decisive by 1943 because someone without the credentials to be taken seriously asked a simple question and tested an unconventional answer. The experts who dismissed his letter learned, eventually, that expertise isn't the same as wisdom. Wisdom is recognizing that the correct answer might come from unexpected sources, that established practice might be wrong, and that testing unconventional ideas sometimes reveals breakthrough solutions. The military officers who initially rejected Browning's technique spent the next 5 decades depending on it. 79 years after Ed Browning wrote his letter to Aberdeen Proving Ground, American soldiers still rely on his technique. Every M2 assembled, every barrel replaced, every headspace adjustment performed in armories worldwide uses the method a Tennessee farmer discovered in 1942. The technique has been taught to tens of thousands of armorers, documented in countless technical manuals, and applied to millions of weapons, yet his name remains unknown. The civilian who couldn't possibly understand military weapons engineering discovered the solution that military engineers couldn't find. The impossible trick that ordnance officers dismissed became standard procedure that made America's most important weapon functionally reliable. And the farmer without credentials proved that sometimes the most valuable expertise is recognizing when expertise is wrong. The M2 that fires today, protecting soldiers in combat zones worldwide, works because one man refused to accept that the problem was unsolvable. The weapon military experts couldn't fix was fixed by someone who shouldn't have been able to help. Sometimes the most important innovations come from the most unlikely sources. Sometimes the impossible trick works. And sometimes the expert consensus is wrong while the untrained civilian is right. The thunder of Ma Deuce, military slang for the M2 Browning, echoes across every American conflict since 1942. But the gun fires reliably, sustaining combat effectiveness through sustained engagements because Ed Browning asked a simple question and tested an unconventional answer. The weapon became untouchable not through brilliant design alone, but through a civilian's insight that expert military engineers had missed. Sometimes the civilian without training sees what the experts cannot. Sometimes the impossible solution is simply waiting for someone to try it.